Okay, so we saw how proper time is related to any other time, proper time being the shortest possible time you measure between two events. Um, and uh, and I guess I should say two causal events because the clock had to be present at event 1 and event 2. If the same clock is present at event 1 and event 2, then that measures the shortest time, and anybody else measures a longer time. So I guess it's got to be a causal event, right? This concept of proper time. If they're not causal events, then there is no proper time. We can show that as an exercise later. But one of the things I want to show you is, not show you. One of the things I want you to notice about this equation that you see in front of you, delta t prime equals gamma t0, is this Lorentz factor is an important factor. It comes up a lot. It's a scaling factor, right? It scales the time, right? So if the time is measured as t0 in one frame of reference, then it's measured as t0 times the scaling factor of the Lorentz factor in another. So the Lorentz factor isn't just an arbitrary factor. It comes up, it's a real physical quantity. Okay, but let's just see time dilation from a different perspective. Let's just do an experiment. And let's say that we have a light bulb on the floor. I'll draw it as a black light bulb. And we have a mirror on the ceiling. Nothing untoward here, just a light bulb and a mirror. We're doing an experiment. And let's say that there is a distance of L between the floor and the ceiling. A distance of L between the floor and the ceiling. And ask the question, how much time does it take the light, if I turn the light on, or if I just have a flash of light, how long does it take the light to get from the light bulb to the mirror on the ceiling and back to the floor again? So we're going to have a flash of light. Bing, flash of light, bounce up, bounce down. How long does that take? Well, if the light goes upwards at C and back down at C, therefore the amount of time that it takes is, right, if it moves at C and it goes L up and L back, then it's going to be distance equals rate times time, right? Distance equals rate times time. L equals, oh my gosh, distance equals rate times time. Okay, but it goes up and back, so the time is 2L over C. The time is 2L over C. Right, so I'll make it for one trip, or meaning for up or down, right? So the total time is 2L over C. So let's just call that in the frame of reference of the light bulb. So let's just say, let's call that LB for light bulb. Light bulb's frame of reference. Okay. So then let's say that this experiment is being done on a train. We love trains, right? The experiment is being done on a train. So in actuality, there's a train car here, and the train is moving at speed v relative to somebody who's stationary on the platform. So let's calculate how much time it takes according to somebody on the platform. So for somebody on the platform, what are they going to see? So let's say how to draw this. So the platform point of view, so I'm going to go back and say, oh, okay, so this must have been the train point of view, and the platform point of view. From the platform, the person sees, and again, this has to be Gedanken because it's so fast, right? But anyway, it's a true experiment. It could actually be done. I'm going to have to draw it a little smaller. The person, actually, let's just draw the light. The person sees the light leave the light bulb, but the light is moving because the train is moving to the right. The light is moving in that direction because by the time the light reaches the ceiling, remember, the mirror had to have moved over, right? The mirror had to have moved over because the mirror is moving at speed v to the right. Okay, so a person on the platform is going to see the light leave the light bulb. Let's just pretend that's a light bulb. And then later on, the light will not have reached the mirror until the light bulb and mirror have moved over. So the light must have traveled along that line. And then again, the light's going to bounce back down, but by the time the light bounces back down, the mirror and the light bulb will have moved over even more, right? The mirror and the light bulb will have moved over even more. Okay. So, but the person on the platform absolutely sees this happen, and they also, because of postulate 2, they still see the light moving at C and the light moving at C. So how long does the person on the platform say that the light's going to move? So in the light bulb's point of view, frame of reference is 2L over C, but the person on the platform is going to see it move 2 times the distance, whatever this distance is, right? Looking back at the picture, whatever that distance is, 2 times distance over C, where distance is equal to, we can go back to the picture and say, oh, okay, so we need to know, in order to figure out this distance D, again, I'm in the picture, the bottom left, I need to know the distance up and down, which is L, and the distance to the side. Now, how far did the light move to the right? It moved L up, but how far did it move to the right? Well, it moved, because the train is moving to the right, it must have moved distance equals rate times time. V T platform over 2, right? The time to get to the ceiling is half the total time, which we already called T platform. So it's V T platform over 2. And so that the distance D, oh, careful here. No, I did that right, sorry. I thought I made a factor of 2 mistake. Where the distance D is the square root of V T platform, I'll just do TPL, T platform over 2 squared plus L squared. Notice what's really important in this derivation. We're showing this derivation because this has nothing in it that has to do with the Galilean transformation, right? Remember that this quantity at the top came from the Galilean transformation, but we are showing an experiment that you could do without the Galilean transformation. We're just assuming postulate 2, right? We haven't used any gammas anywhere. Okay, so we can go ahead now and plug this D into T platform. And so what you end up getting is T platform equals 2 over C times the square root. And then I'm going to, I won't bother writing what's under the square root. I'm going to square both sides and multiply both sides by C squared, because once I square it. So I'm going to square both sides and multiply both sides by C. So we get, therefore, T platform. So we get this. Again, we squared both sides and multiplied by C over 2. Then squared it. Okay. And so then what I want to do is go ahead and solve for T platform. Therefore, T platform is equal to, T platform squared is equal to 4L squared over C squared minus V squared. Do the algebra. It's very straightforward algebra. So therefore, T platform is equal to, we can factor out a C squared on the bottom, which is what we always do, 4L squared over C squared times 1 over 1 minus V squared over C squared. And we can, that's squared. And we can square root both sides. So T platform is equal to 2L over C times 1 over the square root of 1 minus V squared over C squared. Ooh, I hope you recognize this is gamma, right? We did not use the Lorentz transformation. But what do we get? Excuse me. What we get is that T platform is gamma 2L over C. Well, 2L over C, we've just seen that somewhere. 2L over C is T in the train's frame of reference, the light bulb frame of reference. So therefore, T platform equals gamma T light bulb frame of reference. This is that same equation that we started with at the top here, right? T measured in any other frame of reference is equal to gamma times the time measured in the frame of reference, which has the moving clocks. That is so interesting. I think that is so cool that came without Galilean transformation. Okay, and that simply is the constancy of the speed of light. That's what does it. That's what allows for time dilation. The fact that speed of light is a constant, doesn't change when you change reference frames, is what requires that time is dilated. Time changes. Time is not absolute. Done.